Hi everyone, and welcome back to yet another Math Research Live with me, Charlotte Aten. So today I'm going to be talking about something pretty different than what I've talked about in the last couple weeks. So hopefully people are here to experience some topology and lattice theory instead. And so I'm not talking about a paper of mine or something that I'm currently working on per se, but as you can see, there's a linked paper in the chat here, and this is actually a paper of George Bergman, and so I have something that is related to this topic, which hopefully I will be posting within the next week so that I can talk about it during the next live stream. But I thought that I would actually I would prepare to talk about that by instead or first talking about something that I wanted to think about that was related to this paper, or just to this general topic. And so so I'm not going to just dive straight into the question that I'm thinking about poking around at a little bit, but I do have an idea for something new that I wanted to take a look at, or that at least will be new to me, related to this. But I thought first I would actually illustrate the basic construction that is in this paper. Okay, well, obviously I'm not going to sit here and read all of this to you, but let me kind of illustrate for you what is going on here. So first of all, as always, let me know if you have any questions. This is definitely going to be something which is going to take some amount of background, but I'm happy. I'll be here for 3 hours, so I'm happy to answer any background related questions that people have as usual. Well, okay, here's the basic idea that people are probably familiar with. So or well, I guess I can't say what everyone's familiar with, but imagine that we have some kind of lattice like this. And so by this I mean that we have some partially ordered set where we have things that are like 0, 1 for our bottom and top elements, and A and B are two other ones. And if we take just anything at all and do this meet operation with 0, we find the greatest lower bound of anything with 0, we just get 0. If we do the join with 1, so take the least upper bound of anything in 1, well, that's just 1. And then sort of the only other interesting things going on here are that the greatest lower bound of A and B, the biggest thing that's below both of them, is just 0, and the smallest thing that's above both of them is 1. Okay, so that's some kind of algebraic structure that has these two operations. And what this paper has to do with, and what the thing that I will hopefully post soon also has to do with, is the idea of how to go from something like this, which has these this finite set of elements, 0, 1, A, and B, and these operations of meet and join. How do we go from something like that to a sort of continuous version, where you can imagine, if you just look at this picture, that it kind of seems like, well, maybe we should be able to extend those operations in order to define similar operations that are on this two-dimensional square that all of this is filled in. That's the basic idea. Well, there's a question of how to do this, and unfortunately the first idea that you might have is actually not going to work. So if we think about this as being like well, as being this 2D square, one way that we could think about these points in the square is that maybe maybe over on this side we could think about these things being convex combinations of 0, 1, and A. In other words, if I have a point over here, okay, maybe to make this less confusing, maybe I'll change my names and I'll say I'm going to call this maybe call this bottom, call this top, T for top, for true. And then if we look at a point over here, we could think about that point as maybe being, for instance, if it was like maybe right in the middle, it would be like 1/3 A, 1/3 top, and 1/3 bottom thing. Or just in general, we could have maybe, maybe I'll say SA times A plus S top times top plus S bottom times bottom, where these guys have to add up. These guys have to add up to 1. So we could have such a convex combination. So the idea being that like just A by itself is really like 1 times A and then 0 times the other two, and similarly for things in between, 1/3, 1/3, 1/3 would give us like the point that was exactly in the middle, just like averaging them together, and other things would be similar. So we could do this. I mean, certainly we can define such a thing, and then points over here similarly would look like, maybe SB times B plus S top times top plus S bottom times bottom, where again the SB, S top, and S bottom have to add to 1. So we can definitely define this shape like this, like we can make a shape like this. But the problem is that we would like for this shape to actually have the structure of a lattice like this thing had over here. Somehow we'd like these two operations, this meet and join operation, we'd like those to extend to this thing, and unfortunately this doesn't do what we want it to in that sense. And so okay, maybe I'll illustrate trying to do that. I actually remember from doing, since I'm now doing this to get myself back into this stuff, I remember from doing this years ago, like, having made this observation before when I was, first looking at this kind of thing. But now it's been so long that I don't know it off the top of my head, so you're actually going to watch me, refigure out why it is that choosing the sort of obvious extension doesn't work. And again, just let me know, as always, if you have any questions or want to see anything in more detail, and I will be happy to answer that. Or since it's a more topological day, also feel free to post the donut emoji in the chat. It's always fun to do the donut emoji. Here, maybe I'll do. I don't think I ever have done one myself, so maybe I'll do it myself. Let's see if I can recall how. No, I think it's not it. Let's see. Oh, is it this? With these emojis? There we go. Okay, there. Yeah, that thing. Who knows? Maybe we'll have donuts with different number of holes in the future, but for now we have 3. Okay, so why doesn't this work in the sense that we don't get a corresponding lattice structure from this? Well, let's just mess around with it and find out. Well, I guess here's one thing. So in a lattice, we should have that x meet x should always be x. So let's see if we can find a failure of this by just trying some arbitrary thing. We'll go to the next page. So I'll redraw my picture again. So here's the bottom thing, here's A, here's B, and then here's the top thing. Maybe I'll choose this point. So what is that point right there? That point would be maybe 1/2 A plus 1/2 top thing, the thing that's halfway in between those. Well, let's see. If I have 1/2 A plus 1/2 times the top thing, and I wanted to take the meat of that with itself, well, I haven't really defined how to do this on these convex combinations, but let's maybe do what might seem like the obvious thing and try to make this bilinear. In other words, I'm going to assume that this distributes over the addition the same way that like multiplication would. And so it seems like perhaps this should look like something like 1/2 times 1/2 A meet A plus 1/2 times 1/2 A meet top plus 1/2 times 1/2 top meet A plus 1/2 times 1/2 top meet top. And when we do this, well, let's see. This is going to give us A. This is going to give us A. This is going to give us A. And this is going to give us the top element. So what we end up with instead is actually, well, we have 3/4 there. And then we have 1/4 here. And so, okay, so my intuition was correct. So this is actually showing that this can't possibly have the structure of a lattice, because if it did, then this is supposed to be the same thing as 1/2 A plus 1/2 times the top element, but that's not true. The one that's 3/4 A and 1/4 times the top element would actually be like over here instead, and these two are not the same point. One of them is halfway between, and the other one is like 1/4 of the way along. So like they're different. They have to be different. So we can't just like bilinearly extend the meet operation and get another lattice operation. It's not going to work. Okay. So, okay, so that's not going to work. Does anyone have any questions? Any questions about that or anything, just in general at all? I feel like I'm. Oh, I guess I didn't need to do page chat. I feel like I'm. Yeah, and the question can even be, what is a lattice? That's a perfectly valid question as well. I just decided to just dive right into it, but yeah, if anyone wants to know what any of the definitions of things are in more detail, I've been doing new pages and I don't really need to, huh? But yeah, so far I've shown at least that sort of the obvious way of extending the operations to the these convex combinations, they're called, would not give us a lattice operation anymore. Let's see. Okay. Well, let's see, what do I have? I suppose I'll continue on this page. I don't need to just waste paper and use a bunch of use up a bunch of blank space in the computer. All right, so okay, so what would work intuitively? Well, the idea is that what would work is something like this, where we say, okay, maybe I have this thing over here, and I don't know, maybe I have this thing over here. Remember, we're allowed to choose points that are actually on the inside of the square if it's going to be this topological thing that actually is continuous. And the idea is that, well, it seems like the meat of these two things should actually be something like this. Should actually be doing something like that. That seems at least plausible that would work. But the question is basically, how do I describe this in general? Like, how do I actually give a formula for this, and maybe not just for this 4-element lattice I started with, but just for any lattice at all. And so that's actually it wasn't original to this paper, but that's actually what was summarized here. And so here, let me actually just find the summary. So you can do this type of thing with any poset, but I'm just going to talk about what it is for lattices. And well, I mean, this is obviously the goal of this is to do lattices as well, actually, but it's described in slightly more generality. So the idea is that we can actually think about functions from our P will be our lattice in this case to the closed interval 0, 1, so that whenever we look at all of the things in our lattice that have f of that greater than or equal to some number, it's what's called the principal ideal of the lattice. So that's going to be the idea. And so, well, let's look at some examples of what that type of thing would be. So here, if our lattice is that one that I talked about before, that consists of A, B, this top element, and then this bottom element, and then those meet and join operations, then what I would want to be considering would be functions that are going from the set of elements of that lattice, which I'll just, lazily, as the usual lazy thing, I'll just use L to refer to the elements of the lattice as usual. So functions sending this to the closed interval between 0 and 1, which have that additional property that, here, I'll go back to it for a second, have the additional property that that this f sub t, so that's all of the things in our lattice that are greater than or equal to t, that always has to be a principal ideal. Okay, so then I'll show what that actually looks like. So given some number between 0 and 1, this ft, by definition, this is the set of all x's in our lattice, such that f of x is greater than or equal to t. Okay, and so we want that this is we want this to be a principal downset. Okay. And so the claim is that somehow choosing the functions that do that will actually give us this picture and will help us to define the meets and joins in the way that makes sense for this. So that's the idea. Well, let's see. So let's maybe think of some examples of this. So we have to assign a number. So our f would assign a number to each element of the lattice. So rather than thinking about just f as being some function from the set, A, B, top, bottom to 0, 1, well, we can actually just say, well, why don't we just consider f to be, this tuple, basically we can just consider f to be f of A, f of B, f of the top element, and f of the bottom element. Why not? So basically we're considering these lists of 4 numbers where each of these things is between 0 and 1. And then we don't just want any list, though. We want lists with this property. And so, well, in order to figure out what that is going to look like, well, we should think about what the principal downsets of this lattice are. So we're going to have these lists, and they're going to be subject to some condition where all of the x's that are greater than or equal to a given number have to be a principal downset. So we can think about like what that would actually look like. And again, just feel free to interrupt at any time if you have any questions or comments or just want to know more about something. But okay, so in order to understand what this definition is saying, we should probably know what are the principal. Oh, sorry. I said downsets, but actually, I think that I do want. If I'm being careful, then oh no. Okay, I see. No, it's fine for me to say downset. Okay, so there's a question of why did I say downset when the paper said ideal? And well, I guess if anyone wants to hear about this technicality, maybe let me know, because there is actually an important language distinction between talking about ideals of posets versus talking about like poset ideals are not the same as lattice ideals, and so I guess let me know if you want me to talk about what the difference is. But if everyone's cool, then I'll just say that they have to be principal downsets and not worry about what the issue is with this thing. But if for some reason I prefer to use a different word, so let's just go with that, I suppose. So what are the principal downsets of this lattice L that we've been looking at? Well, downsets are the sets that are closed undergoing down in the lattice ordering. So if we look at our picture, our Hasse diagram, well, let's see. So, well, I suppose I might denote it by dn for down. What is the principal downset for the top thing? Well, that's all the stuff that lies below the top thing, and so that's just all of the whole lattice. the principal down set determined by A has two things, which are A and the bottom element. The principal down set that's determined by B is similar, and it has B in the bottom element. And then the principal down set that's determined by the bottom element, that just has the bottom element. Okay. So for each element, the principal down set's just all the stuff that is less than or equal to that element according to this diagram. And A and B are not less than or equal to each other. They don't have any, they're incomparable. They have no relationship with each other. Okay. So the condition then was that if we look at all of the things in our lattice which are greater than or equal to, for which f of that is greater than or equal to a given number, then that should be a principal down set. So, all right, well, let's think about this. So, you know, in principle, right, there are an infinite number of conditions, because we would have to consider, you know, f sub t for t being 0 or 1 over a million, or, you know, like 1 over the square root of 2, or all sorts of different possibilities, right? But, you know, there's only a finite number of x's, and so, you know, we don't really have that many different possibilities to consider, right? So, for instance, let's see. So for instance, if I said that f was like, I don't know. Let's just do all zeros to start with. So remember, this is what f sends to A, B, top and bottom. Well, then f sub 0 is all of the things in my lattice with the property that f of that thing is greater than or equal to 0, and so, well, that's definitely well, it's okay. It's actually true that each of these things is greater than or equal to 0. So that's the whole lattice, and that is one of our principal downsets that we found. So that seems fine. But then if I take like f sub 1/2, for instance, I'm going to get all of the x's so that f of x is greater than or equal to 1/2. But this condition never occurs because none of these are 1/2, or none of these are greater than 0. So this is actually just equal to the empty set, but that's not one of our principal downsets. So this f is not the type that we want to consider. So this f is bad. Okay. So we can't have that. It's not allowed. So, well, let's think a little bit more about this. If I just have some function of the type that I described before, and I'll think about that as a tuple f of A, f of B, f of the top thing, and then f of the bottom thing. Well, if we think about this, that means that what we're doing is somehow we're choosing, we're choosing to take the interval between 0 and 1, and we're maybe arbitrarily somehow we're putting f of A, f of B, maybe f of the top element, and f of the bottom element here. And, well, you know, it seems like the reasonable thing to consider really would be like things like f sub f of a, for instance, right? Because f of a is supposed to be a number between 0 and 1, so we're perfectly within our rights to ask what is the set of all things in our lattice, so that f of x is greater than or equal to f of a. That seems like a reasonable thing to explore. And, well, certainly we know that a is in here, right? Because f of a is greater than or equal to f of a. So we definitely know that this has a in it, and because it's maybe I'll say contains. So we definitely know that this has a in it. But if this is supposed to be a principal downset, then we know that actually this has to be containing not just a but the bottom element as well. So we know that it has to have the bottom element as well, and that actually means that thus we are going to require that f of the bottom element is actually greater than or equal to f of a. Okay. So similarly, by basically the exact same reasoning, we'd also require that f of the bottom element was greater than or equal to f of b, for instance. And so, just by doing the same thing with f of b, and in general, well, if we have two things in our lattice, say u and b, with v less than or equal to u, well, the same reasoning says, you know, if we look at f of u. Well, that's going to be all of these x's, so that f of x is greater than or equal to f of u. But that's going to have to contain u because greater than or equal to. That's going to have to contain u because f of u is greater than or equal to f of u. But that's supposed to be a principal downset, so it's a downset. It's got to contain at least u, so it certainly contains anything that's below it, like b. But then that means that f of v is greater than or equal to f of u. Okay, so certainly we need this to be an order reversing map, and so well, yeah. So that seems like that's definitely a necessary condition. And so, in other words, as we go down in this picture from the top of this thing to the bottom, we should be giving larger values to each of the elements. So, in other words, here we should have, so I'll draw the picture again. So we see that we should be having that the the bottom element gets assigned to something that's bigger than whatever A gets assigned to, which is in turn bigger than or equal to whatever the top element gets assigned to, and then similarly for B. Okay, so we necessarily must have this. Alright. Well, how do people feel about this? Does this seem cool to people? Are we feeling just full of neutrality, or what's going on? Was everyone just really excited to see more of the higher dimensional quasi groups, or are we all just not sure what to say? Okay, well, I suppose that I'll keep at it, but please do let me know if there's anything at all, or just say hi. Just let me know. Just let me know that you're alive and that things are happening. Like I've mentioned before, it's as good as it is for me to look at these things. I actually I work faster when I'm not trying to also explain to an audience, especially when I don't know people's backgrounds. But so it's not as fun to just sit here and talk to myself. So please let me know if you have any questions, or if you just have any opinion on anything at all whatsoever. Just want to say hi. But it seems that this is the point that I've arrived at. Okay. So, well, the next thing that I'm going to do then is I'm going to try to determine whether or not this is a sufficient condition. I know that this is certainly necessary, but is it sufficient? And, well, let's see. So, if I have the bottom element greater than or equal to, well, I sent the bottom element to a bigger thing than A, to a bigger thing than the top, and similarly for B. So what I would want to show is that if I did, I guess I need a new page. So if I did f sub t, right, that's all of the x's, so that f of x is greater than or equal to t, but we can imagine that, we can imagine that maybe, maybe t is here, and we can choose some, oh, hey, how's it going? Do you have a question, or are you just saying hi? Okay, well, let's see. Oh, I want to be consistent with my other thing that I had before. So, okay, so before I had that if let's see, if u is v is less than or equal to u, then f of v is greater than or equal to f of u. So let's imagine that v is less than or equal to u. So then if we have some t here, maybe it's the case that wait, what's it? Oh, a decent way to start by saying hi. Oh my God, Dobby, are you okay? Dobby just made some noise that was concerning.
Are you coming soon?
He's becoming. That sounds pretty intense. All right. Are you fine, buddy? Okay. All right. Dobby. Yeah, Dobby's fine. He's just snorting or something. It wasn't even a sneeze. It was like a... He's too smart for that. You can't pretend to throw the ball at him. He looks at it, but like I've known dogs that will go and chase it like every time. Oh, buddy. Oh, Dobby. No, there's no ball, buddy. He's still too smart for that. It was a fluke.
I tricked it. Oh, yeah. Okay. Yeah? What's that? Oh, yeah.
See, I told you. He'll look in that direction, but he knows that you're not throwing anything. He doesn't believe you enough.
Alright, well, I got him 2 out of 3. So.
Oh, okay.
Good job, buddy.
So, yeah, you're too smart for that, huh, bud?
He's looking at me so bad.
yeah, because he knows that you're messing with him.
Geometry, buddy.
Okay, so anyway,
I'm sorry.
So suppose that v is less than or equal to u in our lattice, then what we found is that f of v should actually be bigger than f of u. And let's imagine that we chose some t that is between those values. Well, then we know that f of v is greater than or equal to t, and well, if we know that f of v is greater than or equal to t, then that means that that v is actually in f sub t, right? But that means that anything that is that means that anything that is less than or equal to v is also in f sub t. Okay. So maybe the way that I should think about this is the following actually instead. Why don't we do it this way? I've got that. Okay. So So let's do something slightly different instead. I realized how I want to do this now. So let's say we want to look at some f sub t, and our goal is to use the condition that we know, which is that v is less than or equal to u, implies that f of v is greater than or equal to f of u, in order to see if that's enough for us to. Well, wait, hold on a minute. This is analysis because I have inequalities. Is I promise that there's only going to be. See, I wrote the function up here somewhere. See, it's really just a tuple, and so it's really, I'm trying to explain how this is actually basically a discrete thing. So don't worry, we're not going to be considering any scary classes of functions on the real numbers or anything. Yeah, no, it's just combinatorics and algebra. Yeah, it's okay. I'm not gonna ask you for any particular like types of I'm not gonna ask you for any kind of continuity or differentiability or anything. Like, just don't worry, it'll be fine. It's just a discrete thing. Everything's discrete. Okay, so the real numbers are just an illusion, you know.
Did I just hear you say the real numbers are just an illusion?
Yeah.
Aren't they like the least illusionary of the numbers?
Oh, that's like a whole. Okay, yeah. So Nova just asked if the real numbers are like the least illusionary of the numbers, but that's definitely not true. Because people get quite agitated actually about like what I mean, okay, like everyone agrees that like the construction, various constructions of the real numbers are useful, they're important and useful ideas, they're very helpful for doing practical things, but like, if you look into it, you'll find that most real numbers are actually undefinable. There's no way to write down any kind of, not just a formula, but just any kind of expression in any language that we could even in theory design which can specify almost any of the real numbers. And so that's like a big problem, first of all, because that means that even though there's so many real numbers, we can't actually make use of most of them. Even certain practical ones, like I think it's pronounced Chaitin's constant, can't actually be computed for in a, you know, there's, maybe I won't get into it right now, but like there's there are constants related to programming languages that people actually use where knowledge of that number would be useful, and we can't you know, we can't compute them, and like it's just there's all sorts of weird real numbers that just are like really
I can handle those.
yeah.
Okay.
It's okay. Nova's tapped out. All right. It's the real numbers are scary is the point. So, all right. So let's go back to explaining why I don't actually need to know about what all the real numbers are. Okay. Okay. So we know that we have this condition. Now suppose that here we have let's see. So we know that if v is less than or equal to u, then f of v will be greater than or equal to f of u, right? So maybe here's f of v, maybe here's f of u, right? And so now imagine that, oh, the printer's going. Imagine that this u was the first one. So there's no other f of anything that's in between here, right? This is the first one that comes up, right? There's got to be a smallest thing. Well, in other words, suppose that that u is the minimum thing among the set of all x's in our lattice, with the property that f of x is greater than or equal to t, right? There certainly must be such a thing. There has to be such an element as this, because there's only finitely many things in our lattice, right? But then this condition is telling us if v is less than or equal to u, then f of v is greater than or equal to f of u. So that is telling us then that if v is less than or equal to u, then that is going to imply that not just the f of v is greater than or equal to f of u, but it's also going to imply that f of v is greater than or equal to t, and so that in turn means that actually v was an element of this f sub t. And if you look at it, so if you look at it, that means that if we look at the first thing that's where f of that thing is greater than or equal to t, then we know that everything that lies below it has to be in this f sub t. Okay, so certainly we know that in this case f sub t has to actually contain the principal downset determined by that element u. That was the smallest thing. That was the smallest. Oh, I see what I wanted to actually say here. So what I meant by the smallest thing was actually okay, let me rewrite this. It's probably clear from the picture what I meant, but I was being sloppy when I explained what this was. So the thing that minimizes the set of the f of x's where f of x is greater than or equal to t, where x actually has to be in the lattice. So, in other words, I want the thing in the lattice that makes this f of x as small as possible while still subject to the constraint that f of x is greater than or equal to t. And so I know now that means that for that choice of u, this f sub t has to contain that downset, that principal downset determined by u. So that's necessary. Okay. So I certainly know that has to be the case. But maybe it's possible. Yeah, so I mean that look at all of the f of x's with f of x greater than or equal to t. Choose the x that makes that gives us the smallest possible thing. That's what I, okay, yeah. Sorry, that's hopefully that's the closest to analysis that I'll get. This is people also call this, in case this makes it better, people also call this like argmin. So you might see like that instead. Like choose the smallest x in the lattice that makes that go. Yeah. That's what I meant. Like argmin. Okay, so certainly we know this, and also notice that okay, so notice that we have that, but then also notice that it didn't really matter what t was as long as like this f of u. Oh, well, now you know. It's really crazy how sometimes you can go a really long time without having good notation, and then you see it, and you're like, oh, I can't believe I never thought to use a note. Even if it wasn't the same one, like, why didn't I choose notation for this? If I had chosen good notation, oh well, yeah. I mean, as long as you have some way of expressing it, but sometimes it's like you just don't have anything, or you just like, keep explaining it in words and thinking, I don't really need the notation. But once you have the notation, you're like, oh, everything is easier to think about this way. Like, it just really, sometimes notation is really, really what sells it. But, okay, so, yeah, so, I mean, can you imagine being, doing combinatorics without this? If you had to every time write, write that instead, like that would be, you'd be done. You'd have no hope. Like that's way too much. So yeah, let's not do that. Okay, so let's see. So what if we concluded at this point is that if I have such a function, then well, certainly we should have the downset of u, where u is this first thing that comes up here. And okay, well actually I kind of I did this for psychological reasons, I guess, so we should have that whole downset. But you remember, this doesn't go the other way necessarily. So it might be possible that there's something which is not less than or equal to u, but which f of that thing is bigger than f of u. Like that's conceivable, right? So so all that we know for sure is that this f sub t contains the downset of u, and actually, well, it has to contain the downset determined by, if you think about it, it's like the exact same kind of argument, just assuming that f of u is bigger than t. If we just choose some other u that's just f of that is bigger than t, then similarly it has to contain the down set of just any w where f of w is greater than or equal to t. Okay, but then if we think about what this looks like, so what this is saying is basically for each t, there's going to be a finite set of points that have a bigger value. F of those points is a bigger value than t, and that has to be a principal downset, and it has to contain the downset determined by anything else. So let's think about how this could happen in our example. So in our example, remember, it looks like this. And so, well, how could we actually assign these values between 0 and 1? Well, since the bottom element is in all of the principal downsets, it's going to have to be somewhere up here, right? So f of the bottom element is going to have to be somewhere up here. Similarly, everything is contained in the downset for the top element, so the top element's got to have a pretty small image up here. And now for A and B, well, let's see what happens. So if okay, so let's see. So like, what if we have like f of A here and f of B here, right? So if we did that, then, well, if we chose a t that was here, then our downset would just be the bottom element. And if we chose t here, we get b in the bottom element, which also is a principal downset. It's the one for b. But we'd have a problem if we chose t to be here, because then we'd get a, b, and the bottom element. And the reason why that's a problem is because this is not a principal downset. There's not a single biggest thing that all of these things lie below that's in this set, right? It doesn't look like all the stuff below a single element that is in this set. So that doesn't seem like it can be the case. So in other words, we shouldn't be able to have this. But since we know that f of A and f of B have to be between the bottom and the top, then, well, what configurations are possible? So one thing that's possible is that, well, I guess first of all, I should make one other point as well. So there's actually something bad about choosing t here, which is that set f sub t will actually be the empty set in that case. And so that's not allowed either. So, because that's not a principal downset. And so what's going to happen is that this f of the bottom element actually has to be 1 in order for this to work. And for the f of A, well, there aren't too many possibilities, right? We could either have well, okay, let's think about this. We could either have so we can't put f of A over here for the exact same reason that we said before, like symmetrically. We can't even make f of A equal to 1 because we'll still have the same problem. We'll get B, the bottom element, in A, and that doesn't work. So we can't have that. On the other hand, what happens if we put, like, what happens if we put f of a over here? Maybe we make it the same as the top element. Well, then we actually get something that works, because if we go here, we'll get the down set that has b and the bottom element, and that's okay. If we go choose a t over here, we'll just get the bottom element. That's okay. And then if we choose a t that is over here, then we're going to get all 4 elements, and that is a principal down set too. And so it seems like this kind of configuration can work, and A and B are symmetric in this way. So that means that the only valid choices of f, so where I said it was like f of A, f of B, f of the top element, and f of the bottom element. So this works according to our rule when what? F of the bottom element has to actually just be 1, and then either f of the, oh, I wrote bottom element over here, but I meant top. So I should reverse the ordering. And either f of the top element is equal to f of a is greater than or equal to f of b. Oh, sorry, is less than or equal to f of b. Or f of the top element is equal to f of b is less than or equal to f of a. Okay. So those are possibilities, and I claim that this actually looks geometrically like what we would expect. So let's okay. So let's think about this. Maybe on the next page. So okay, so here's the bottom, top, A, B. Okay, so let's do the f of the top thing equals f of a case first. So then in this case we'd have a tuple which looks like, so our f of a, well, just get so right, f of a, and then whatever f of b is, it has to be smaller, or it has to be bigger rather, and then f of the top thing, which is also f of a, and we actually know f of the bottom thing is 1, so that's always going to be 1, and it's not really very interesting. Okay, so what's a typical choice look like? Well, let's choose a to be 1/2. We need f of b to be something that is bigger. So maybe f of b is, I don't know, 3/4, and then that's just the same thing as what f of the top thing is, and then this is 1. Okay. So, well, how am I supposed to interpret this then? Well, okay, so that's what a typical thing looks like, but let's first look at the extremes for trying to understand what this is saying to us geometrically. So, well, let's see, the smallest thing I can choose f of a to b would be 0, and then I could choose anything that was greater than or equal to 0. Maybe I'll just choose 1, and then I can choose, and then f of a has to be 0, I'd have that. Or I could have chosen f of b to be as small as 0 and gotten that. Or, let's see, I could choose, or for instance, I could choose like f of a to be, well, as big as 1, and then this would have to be 1, and then this would have to be 1, and everything is 1. But, okay. So, I suppose that those are the extremes that I could have, and so yeah. So there are 3 of them, and I guess the idea that I want to give is that this should somehow correspond to those convex combinations that I mentioned earlier. Let me just turn that off. But okay, I chose this arbitrary example in a misleading way, but these first 3 coordinates don't have to add up to 1. I could have this be 1/2, and then this be like 9/10, and then this be a half, and this be 1, and that will still work. All right. So, okay, so that's the f of t equals f of a case, and then similarly there would be the f of t equals f of b case, and so maybe looking at that will be illuminating as well. I'll just draw my picture again here. Okay, so this is the exactly symmetric thing, right? Oh, I guess I did have more room. I keep thinking I don't. Well, here, let me just move this up. Why not? You know, believe it or not, I actually wasn't sold on this journal program until after the pandemic. I always found Zoom to be enough, and then I finally really tried messing around with this, and I was like, oh, I understand. Okay, so we still have to always send the bottom element to 1, so there's no way around that, and well, what do we have here? So we have to make well, I guess I'll just give that same generic picture. We have to have f of a be greater than or equal to f of b, but then f of b and f of the top element are the same, and then this is still number 1. And so we have exactly analogous examples, right? Where we can do 3/4, 1/2, and then that has to be 1/2, and then that has to be 1. And then what are the extremes? Well, let's see. So before I made f of a 0, but now if I make f of b 0, then this has to be 0, this has to be 1, and then let's see, so then that has to be, or well, then this can be whatever I'd like. I can make it as big as 1, or I can make it as small as 0. And similarly, just like I had up here, I could also make f of b 1, in which case f of top is 1, this always has to be 1, and I could even well, then I would have to choose that to be 1, because it has to be even bigger than this. Okay. And so, and then of course I can choose other combinations of things as well, as I did over there. And so then what I want to point out is so this one this one is putting, there's always a 1 on the bottom element so that it doesn't really tell us anything, but this is putting a value of 1 on, this is putting a value of 1 on the bottom element, or not on the bottom element, on B, and it's got zeros everywhere else. So, you know, we actually might think of this as representing B, and then similarly, over here, this has a 1 on f of A and zeros everywhere else. That's interesting. And so we might think of that actually as like A. And well, then what are these other points? So we might think of having a 1 on only the bottom element as being like the bottom element, and having sorry for the too many arrows, but having all 1s be like maybe this top element. And notice that this is compatible with the ordering, right? That if I just do the component-wise ordering, well, 0 is less than 1, and so bottom is less than B. And then here we have 0, 1, 0 versus 1, 1, 1, and so B is smaller than the top element. And then over here, we have a similar thing where this is like the bottom element, and then this is like the top element over here. And so then these other things would represent points that were somewhere else in between. So we could think about like, okay, this has like, so 3/4 to A, and then, you know, 3/4 to A, and then we're giving 1/2, we're giving 1/2 to, well, to B and the top element. And so we could actually well, we could actually identify that with some combination of these points here, right? Because well, this is always just going to be 1, but maybe if you just ignore this last component here, right? You could think about this this point as being like, you know, as being perhaps this combined with this. Yeah, because I need my f of A to be bigger than my f of B, so I could just take like 1/2 here and then 1/4 here, and so well, that's the idea. So I can actually identify some arbitrary point with a convex combination of these other ones. If I forget about this last coordinate, right, I can say 3/4, 1/2, 1/2 is equal to well, 1/2 times 1, 1, 1 plus 1/4 times 1, 0, 0. And then this isn't a convex combination because the coefficients don't add up to 1, but I can also say plus 1/4, 0, 0, 0, and now that is a convex combination. And so this would be saying like this point that I chose here, it's like if, you know, 1/3, 1/3, 1/3 would be right in the middle, right? So it's actually more in the direction of the top element, and it you know, so it's maybe more in the direction of the top element, but also a bit in the you know, the same amount in the direction of 0, 0, 0, the bottom, and 1, 0, 0, which is like A. And so perhaps the corresponding thing would be somewhere like this. So or you know, if you want to stick on the extra one coordinate that just doesn't ever tell us anything, it's whatever. Yeah, so that's the idea. So that's maybe so that's maybe a bit more in the direction of the top element. But of course that's not surprising because it's got bigger values for a lot of the entries. Yeah, and so so notice that this element that I chose, this 3/4, 1/2, 1/2, 1, if you want to include the one that never tells us anything at the end. If you'll notice, assuming that my picture is pretty correct, according to like the sort of obvious ordering where we order component wise, this is well, it can't be bigger than A because 3/4 is less than 1, but 0 is less than 1/2. So this thing and A are not comparable to each other in that sort of obvious or extension of the ordering. So neither one is bigger than the other one. This one's a little bit higher in the picture that I drew, but neither one's bigger than the other one in that sense. So here's the idea. So now I've finally done enough that, assuming there's no questions, people have been quiet today. I don't know. I don't know if what's up with that, but just let me know if you have any questions. Maybe it's just because this is it's Labor Day. I forgot that it was Labor Day. Happy Labor Day. Well, you know, not everyone's American, so maybe I was so confused. I was like, I feel like it's really not very active today, but I now realize that many people are probably Americans who watch me, and it's either Labor Day for you, or you're not in America, which increases the probability that you are somewhere where you're not awake right now. Okay, it's all coming together. I'm figuring out many different things at once here. It took me about an hour to figure that out. I thought of it earlier today too, but I was like, no, I'm going to do it anyway. Like, there's plenty of people who aren't American or who aren't going out or whatever. And I just couldn't figure it out. I was like, wait, what's going on? Yeah. Okay, so now I understand. All right. So anyway, this is what I'm doing for my Labor Day weekend. So anyway, we have now reached the point where oh yeah, I don't know. I mean, okay, so to be fully honest, I'm gonna do a thing about Labor Day now. So here's my my type 5 on Labor Day or whatever, right? I've never actually done stand up, so don't worry, it's not even gonna be 5 minutes long. So for many years I couldn't figure out the difference between Labor Day and Memorial Day because like if you look at the details, they do have different themes, like they're about different things. One of them's more like about the military or something, but it's that they have almost the exact same rituals associated with them. It's like summary kind of stuff, like you have like, you have like a hot dog and like you wear a baseball cap and like you go out to the park or whatever, like, and you're with family and friends and like there's a barbecue or something, like that's like the vibe that they both have. But what makes it even more confusing, it's also like there's no specific ritual beyond this. So like there's no other really specific thing. Like, oh, maybe no, there's parades for both of them. I think. Okay, I'm not 100% sure, but like I think there are parades at least for one, but I think both. And it's just like, as a kid growing up, it's like the same thing. It's like maybe there's a parade occasionally, but it's not like a thing that people religiously have to go to. And so, it's just hard to remember which is which. And then there's no other tradition. Like, there's no other specific thing you do. It's not like Halloween where, like, it's the one where people dress up and there's candy and, like, there's nothing that distinctive about it. And so then, to make it worse, Memorial Day and Labor Day are like the ends of the summer. And so one of them tells you that summer has begun, and the other one tells you that it has ended, and people actually use this to determine like when school starts, more or less, and this type of thing. There's something about you can't wear white after one of them, but if you don't know which one, then it doesn't work, because then, and why, I guess it's because you'll get food on your clothes, or I'm not really sure, but like, it's like they're almost identical, and so it's like trying to remember like which one is the solstice and which one's the equinox or something like that. You know, like it's like there's some kind of symmetry, and like you just never remember. So like right now, I know that Labor Day is the one in the fall because it's today, but whether or not I'll know that in 6 months is very, I'm not sure. Like I'm not really sure whether I'll know it then, because it's so hard to remember. Yeah, and they're also both breaks from school, right? And so you know that they're not the same as like Flag Day or Veterans Day, because you don't get those days off from school. But like it's like then it's like it's very similar, because I think Memorial Day is the one that's like the Veterans one. But like, what's the difference between Veterans Day and Memorial Day? I'm sure one can look it up, and there's some kind of explanation as to what the difference is, or they have different origins. But like, they both seem like general military holiday. I don't know. So we have a lot of these, and it can be hard to keep track of them. I've probably forgotten one that I don't even. Oh, President's Day. But President's Day is special because that's the one that all the car dealerships do all of their car dealership deals on. Why this is, I have no idea. Maybe that I don't know. I like, why not have Flag Day car dealership deals or something? I have no idea. that works for that one, I guess. But like, I mean, why should like a Toyota or a Nissan dealership like have any, you know, like what? I mean, they're not in the business of naming cars after presidents, right? Like, oh, Fords. Okay, now, are those two Fords related to each other though, or is the President Ford and the Ford Automotive Company the same thing? No, they're not. Okay, that's going to be annoying for future historians to try to disentangle, I guess. Well, anyway, holidays are a real mystery. We do get new ones occasionally and get rid of old ones, but it's really an inscrutable process. Okay, so in any case, yeah, the summer is coming to a close, and I've refigured out why it is that these functions that have this property, these sets f sub t are all principal downsets. I figured out, at least in this specific example, why they represent points in the convex hull of these guys. I've done it. I've refigured it out. And so why did we do this? Yeah, yay! I figured it out. So why did we do this? The reason that we did this is that then, if I say 3/4, 1/2, 1/2, 1 is defined to be, or sorry, not is defined to be. If I want to define the meat of that with something like 1, 0, 0, 1, if I want to define that, you know, by definition, if that's supposed to be the minimum over each pair of coordinates, like minimum of 3/4 and 1, the minimum of 1/2 and 0, the minimum of 1/2 and 0, and then the minimum of 1 and 1, which is boring. Then, let's see, I get 3/4, 0, 0, oh, not 0, but 1. Okay, and so, so now if I look at that, that itself I can think of as representing a convex combination, where again I'll just ignore the last coordinate, which is always 1, because it just doesn't affect anything. And so, well, what is that giving me? Well, it looks like I have 3/4 combined with 1, 0, 0, And then, okay, well, maybe not anything else, but I could say if I wanted to, plus, you know, 0 times 111, plus 1/4 times 0, 0, 0. Okay, so now that's a convex combination. And what convex combination is it? It's the one that's on the line between this 1, 0, 0, which is like A, and this, which is like the bottom. And it's like 3/4 of the way to A. So in other words, 3/4 of the way to A would be like here. So this looks like the spot that's supposed to represent A, meet 3/4, 1/2, 1/2, 1. And then if we look at this, that's actually like the picture that I drew at some point before. And so it's like we sort of found the thing that if you think about doing the sort of the orthogonal projection, if you want, onto this, it's this thing that does lie below both A and this point in that point-wise ordering, right? 3/4 is less than or equal to 3/4. 1/2. Oh, or sorry, yeah, not 1/2, but what is this point? 3/4, 0, 0, 1. Okay, so that point is 3/4, 0, 0, 1, and well, as you can see in each of the coordinates, 0 is less than 1/2, 0 is less than 1/2, and similarly, A is like 1, 0, 0, so 3/4 is less than 1, 0 is less than 0, less than or equal to 0, and so forth. Okay. All right, so any questions about any of that? Okay, so that's not a proof, but that's refiguring out the intuition for why this is supposed to work. Of course, once you know this, you can stop writing all of these 1s as the last coordinate because it doesn't matter. But that's the idea. And so the claim is just basically that this works for just any finite lattice that you have, and you'll be able to define meets and joins. So maybe I should do the join of these two as well. You can define meets and joins this way. So maybe I will do the join of these two also. So here I'll do the join as well. Maybe I'll make a bigger picture. Okay. So here's the bottom element, which we think of like 0, 0, 0. I'm going to stop writing the last coordinate. Here's the top element, which we think of as like 1, 1, 1. And then here's the element that's A, and we think of that as like, which one is 1, 0, 0. And then we also have the element B, which we think of as 0, 1, 0. Okay, I guess we also don't really need to include the value of the top element either, since we can deduce it from this. But let's just leave it for now. Okay, so well, before I said that if we looked at I'll draw my line down the middle here. So before we looked at a point that was like this, and that point was, it was 3/4, 1/2, 1/2, if I remember correctly. Yeah. Okay. So then if I want to take so I took the meet with A and I ended up down here. So that was, okay, this isn't a very good drawing, but that was, there's a right angle here actually. So that was the meet, and so that point would be A meet 3/4, 1/2, 1/2. And then if I want to compute a join 3/4, 1/2, 1/2. I should be able to do the same thing, but with max instead of min. And so, by the definition, this is the same thing as 1, 0, 0, showing this. And then this is, well, just the max of each of the components. And so, well, what's bigger, 1 or 3/4? It's 1. And then what's bigger, 0 or 1/2? It's a half. And it's a half. Okay, and so then if we look at this, well, we can think about this as being like, let's see, so what do I want? I would want 1/2 times 1, 1, 1 to get the 1/2 on each of the components, and then I would want another 1/2 just on 1, 0, 0, and then finally I would not have anything else, and so I'd have 0 times 0, 0, 0, and so that's like the thing that's halfway between our A and our top element, and that's like here. And actually, remember that what was that point? 3/4, 1/2, 1/2. That was the thing that was like. Well, it was like 1/2 worth of the top thing, and then 1/4 worth of the bottom thing and A. And so if you actually draw this out carefully, you can see that we get this little like rectangle here. And so the join is like what's above these two, the meet is what's below these two, and so that's A join 3/4, 1/2, 1/2. And so I probably won't go through the whole general argument here, but the claim is that this works. So if you take any finite lattice and you define these tuples or these functions from the elements of the lattice to the interval of 0 to 1 that follow those rules, then those will exactly correspond to these points in like sort of what the obvious picture would be for the lattice, although what the obvious picture is maybe is a little misleading of a name to give it, but there's a natural thing that it corresponds to, which is the order complex of the lattice, which in this case would just be the square like I drew it. And and then the meet and join being defined like by these like mins and maxes does actually do what it's supposed to. Yeah, they should have called them obvious transformations instead of natural transformations. Then everyone would have felt really ashamed when they didn't understand what an obvious transformation was. Yeah. I wonder if that's the motivation behind simplex, simplicial. This has got the word simple, simple. Oh yeah, even simple, Oh, you don't understand what all the simple algebras look like? They're the simple ones. Like that's that's as basic as it gets, really. Yeah. I did talk about simple quasi-groups in another stream. That's right. There's a lot of simple quasi-groups, like a lot. They're just all over the place. But okay, so all right. So now that we know all of this and maybe believe it, what is it? Yeah, I don't recall off the top of my head. But it was. Let's see. I'm trying to remember like what all the chat was about, because we often end up chatting about things or having digressions that are like really detached from from what it is that I am officially talking about. So I can't always remember which different random conversation had to do with which mathematical topic. Oh, okay, yeah, that's fair, honestly. But yeah, you bring a good energy to the stream. Yeah. So yeah, definitely appreciate that, and also that you showed up on Labor Day of all days. Okay, so now we have all of that, and what is it that I what is it that I want to do here? Well, I wanted to think about how, with this example, I want to think about the relationship, like, I want to see if I can have a different way of thinking about the relationship between, let me think about this. So it's like, I want to think of a different way of thinking of this, is the most basic thing that I want to say. And so, so the idea is that, you know, I can think about that picture that I drew up there. Oh, good. Yeah, that's a good thing to go to the grad student picnic and steal cookies. You should eat all the free food that you can as a grad student. It will keep you alive and you'll be able to prove more theorems that way. Now, I mean, you might need to drink water and other things as well. I'm not saying that food is the only thing that will keep you alive. Yeah, but at the very least, you should try to eat food. Hey, Dobby. Dobby eats food every day. Although sometimes he's a little nervous and it takes him a minute. But we put some... Oh, yeah, you gotta drink water. Hey, buddy. Do you want to watch me drink water? Dobby. You want to come up here and watch me drink water? Yeah. Oh, it's Dobby. Oh, there's his nose. So, I know this is maybe controversial, but if I didn't have to breathe and I could live without breathing, I think I would choose not to. It feels like not, like it's not really enhancing my existence. It's just like a burden, you know? Like I would still eat food for fun. I don't know if I would do it every day or what the parameters would be exactly, but I would still eat food for fun, but I wouldn't breathe if it was optional. I think I would just sit there still until I was ready to do something else. I don't know. It just feels like the right way. Yeah, like, and the other thing is I have no sense of smell, so like I can't smell the air. I can't like take like a deep breath of something that smells good, so like it just does nothing for me. It's just I just have to do it in order to function. Like, I can still taste food, just not as much as, like, people who can smell can, but, like, yeah, I mean, like, I just, you know, yeah, so, like, food is less enjoyable. It's still enjoyable, but, like, less enjoyable, so that's why I'm like, yeah, maybe I'd eat food sometimes, like, as a treat, but, like, you know, if it was optional and I would just be fine without it, like, I'd be like, I'd do it less, at least. But, like, yeah. Okay, so what is the question that I wanted to ask about this? Well, you know, the idea is that what we have here is, in this shape, is as though we had actually made, we'd actually gone from this lattice as like this discrete thing that had just these 4 elements. So we had gone from, oh, that's not where B goes. We had gone from this discrete lattice to, we had gone from this discrete lattice to this shape, and it happens that the shape that we made is actually what is known as the order complex of our lattice. So this is a discrete lattice L. This is the order complex of L. And so the idea is that these triangles correspond to maximal chains in the original lattice. So this one corresponds to the chain bottom is less than or equal to A is less than or equal to top. And this triangle, that filled in triangle, is bottom less than or equal to B less than or equal to top. So that's the order complex of the lattice. And so every point is in one of those 2 triangles, or it lies on both of them. And so those are exactly these points that I was getting here. Oh, hey, what's up? I hope you're having a good Labor Day, if that's a thing that you celebrate, which I didn't remember was today until earlier in the stream, because I just forgot. even though I was thinking about it earlier today. You can have a good day if Labor Day is not a thing you celebrate too. But you may not know what it is if you're not American. I don't know if people have Labor Day in other countries. I barely, as I was explaining previously, I barely know what it is in this country. Okay, so... Oh, you got in a Twitter beef about Labor Day, or...? I've heard of May Day as a holiday, but I don't actually know what May Day is at all. I would guess it would happen in May, but this is making it sound like maybe it doesn't. I don't know. I'm sorry. I don't know what May Day is. Oh yeah, I'm sure that sounds 100% American. that the American working class should be separated from the working class in the rest of the world. That sounds like something that Americans would come up with. Okay. Oh, so it was in May, probably, then. I should learn about these things at some point. But yeah, no, I'm not surprised. I'm not surprised. No, I mean, yeah, I appreciate any info that you have to share. Many of these things you learn about it and you're like, oh, that's, it was designed that way in order to like punish like some like labor organizers like 100 years ago or whatever. Like, yep, that sounds like America. Well, in any case, I guess I don't know. Okay, wait. Now I have several things to respond to. So, okay, so the controversy on Twitter was that, okay, so you disagreed with the top mathematicians are 100 to 1,000 times better than the average mathematician. So yeah, I don't know exactly what your argument was, but I definitely agree that well, okay, so I think that the notion of better in math is quite subjective. I do think that there's some somewhat objective things that can be said. But I think that in practice, what happens is actually extremely subjective. Speaking of the thing with Labor Day and like the, separating the working class in America from the other working classes, like I do think that there's like a real like class or like privilege component to like who gets considered. Like, okay, yeah. I'm not gonna get all. I told you that I one day might turn into an angry communist, but that won't be today. So I just will say that. Okay, well you can be a communist on your own stream, Nova. Okay. So I will say that I think that this definitely intersects with it intersects with privilege in a few different ways, right? So like I do believe that if you asked me to like look at two people, are you okay? What happened? Oh no! Did you?
I was dancing a little bit and I bent back my thumb completely halfway.
Ooh, are you okay?
It bent back pretty bad.
Oh, dude, should I?
Are you looking at?
Okay, I have to go act as a physician for a second. I'm sorry, and then I'll tell you my political beliefs and talk about simplicial sets.
See that line?
Okay. No, it's not. There's no separation, right? Can I look at it?
It looks different though, right?
It looks different, but that just happens.
Do you think it's
working part? No, just keep an eye on it. Maybe put some ice on it.
And the pain's already going away.
Okay.
I think I just freaked out.
All right. So, it's not an emergency apparently, and everything's fine. So yeah, I've given my not informed medical advice. I'm not that kind of doctor. Yeah, nails are scary. But okay, so I'm not gonna like really do like super intense politics, but it's probably not too controversial that people who start off life with various kinds of privilege tend to acquire more of it. And so in addition to people's perceptions being colored by things such as where your degree is from, you know, who you know, this type of thing, like independent of your actual performance or credential, you know, your not credential. I mean, I guess I am talking about credentials, but independent of your individual achievement, right? People will have these preconceived notions. They've been primed because like Harvard is a brand name, whatever, right? Like household name, you know. Like there's no avoiding that. But in addition to that, it's true that people who have access to more money don't have to work for money so much, have more time to study and think about math. And so people who start off with a lot of privilege will tend to acquire more of it in a virtuous cycle. And so regardless of that person's inherent ability to do math, whatever exactly that means, people who start off more wealthy and more privileged in terms of, you know, whether it has to do with like physical ability, you know, money, as I mentioned, even just like social acumen, you know, like higher social standing because of various forms of, you know, privilege or discrimination, those people will have more time to study math and they'll be less stressed out while they're doing it, and they'll get better at it, and they'll you know, observe more things and, you know, be more aware of what's going on. And then people look at them and say, okay, you know, you can say that, you know, they started off wealthy and they have, you know, they went to MIT or wherever, but they're also very good. And so this is also how the system reinforces itself, right? Because then when people complain and they say it's not fair, that person had every advantage. I'm, you know, working at this gas station while I'm trying to make ends meet or whatever. I'm just giving that as an example. I've never worked at a gas station, but, you know, like people do these things, and then like it's true some of those people will make it, but maybe not most of them. Whereas, like, you know, there are people who have every advantage and fail, but it tends to really skew in the direction of the people who already had those advantages. And then people can say, oh, look, it's a meritocracy because, like, some of the people who had a hard time succeeded. Like, my new postdoc mentor now, like, he worked to put himself through college, and so, like, he made it, and he became very successful. But, like, that doesn't, you know, that may be, you know, an exception. That doesn't prove that everyone can do that, right? Like, even other things being equal, like inherent ability, right? Yeah, I mean, it's exactly. So that's kind of my position on this, is that there is so much noise around what constitutes mathematical ability that I think when people talk about this, they usually mean inherent skill or inherent ability, and I think that that's not really. I'm not going to say that it doesn't exist, but I am going to say that I think that it is very misleading, because like the reality is just that if you take a grad student who's in a prestigious university from a very privileged background, that person is going to just literally have spent so much more relaxed, comfortable time studying mathematics. That's basically guaranteed. And so it's like apples to oranges. If you take someone from a poor background at a less known university, like it's, you know, it's yeah, I mean, it's just, yeah. So I definitely agree with this. Like, okay, sorry, that's probably more than enough, but I definitely agree that you can't compare people like that. Like, and for that matter, you can't look at a 10-year-old or even an 18-year-old and say whether or not they're going to produce great research. Like, that's just not going to happen. It's just, you know, I know that a lot of people don't believe that or don't feel that way, but I mean, just there's so many people who were taking grad classes when they were teenagers or in their early 20s, and they just burned out and did nothing. Like, yeah, I mean, why should mathematical skill be a one-dimensional thing? wouldn't you imagine that something that's so like multifaceted and has so many different connections to so many different areas would not be like a one-dimensional thing that you're either good at or you're not good at? Like, doesn't that seem consistent with like reality, just the rest of reality? Yeah, but I mean, it goes back to all this stuff of like IQ and like, you know, people wanting there to be this single measurement that, you know, determines if you're successful or whatever. But yeah, anyway, I've probably said more than enough about that. But the other thing, I didn't want to ignore this. The other thing was this order lattice reminds you of the order you put on vertices of writing out simplices and simplicial sets, and that's actually what I wanted to think about. Assuming everyone's good on hearing about my position on like who's good at math or whatever. I guess I'll say one more thing before the simplicial set thing, which is that obviously I would like for people to okay, this is also the other way that this bad thing gets reinforced, right? Is I need people to believe that I am good at math, whatever that is supposed to mean, that not just that I'm good, but that I'm better than other people, because if they don't believe that, then they might not hire me for a tenure track position, right? So like, I need to reinforce this social thing, this social construct of who is 1,000 times better at math, in order to make sure that I keep getting jobs. And so it's like, you know, you can't really, like, if I really rail against this too hard, I risk, you know, contaminating my possible group of people who would hire me for a tenure track job, because they'll say, you know, she's probably being like that because, you know, she's not really good at math and we found her out, you know? So, you know, I can't rail against it too hard. Or maybe what's worse is, even if I am good, maybe I'll successfully demonstrate that actually there's a huge social component to this that's similar to becoming a famous or successful artist, and that, you know, it's just reflecting some existing privileges that people had. Because in case, you know, if you've watched me for a while, you probably know I'm not from a wealthy background, but I was lucky to be from a poorer family in a place that had a lot of rich people, right? Because I'm from New York State, not New York City, so I wasn't around all the billionaires and everything, but I'm from New York State. And so because of that, I was close to universities that had more of these people who had the, you know, opportunity and you know, desire to learn math and do math very well and everything, and so I was able to, you know, reach where I am now. But someone who had more disadvantages than I had may not have made it, and for what it's worth, I only made it to where I am now because of some federal government programs when I was an undergrad that helped me to make it to the next stage, you know. Not like, you know, well, anyway, maybe I won't go too much into all of it, because it's maybe too much of an aside, but like, I had a lot of help when I really needed it. Yeah, I mean, is there a lottery? Wait, are you saying you won the lottery to go to college, or is there a lottery to see if you can get college paid for in Florida? I don't know how it works in Florida. Okay, I'm not sure how it works there, but yeah. I mean, it's like you've. Oh, okay. It's oh, right. Most states do that. That's right. I think even New York does that. Yeah, I remember hearing about this now. Yeah, it's like you've got. It's not enough to be passionate and to be dedicated. You also have to be lucky. You have to be lucky enough to get close enough to where there's people who are powerful enough to put you into the next stage. Otherwise, you're just done before you started, which is really awful. But that's how it is. Well, anyway, I don't know what to do about this, or if I can really save the world by saying these things or anything. But yeah, that's kind of my take on it. So, you know, I guess I'll say one other thing. I hope that watching me do this has made you more confident in yourselves and not just less confident in me. That, you know, sometimes I make mistakes or forget things or whatever. Like, if you talk to people who are super famous, who are very well known for whatever thing, you will eventually watch them make mistakes, forget things, or not know things that you thought that they should know. Like, that's 100% going to happen. Like, in my experience, there is no one who is superhuman in the manner that people imagine. Like, that's not something that I've ever experienced. And I'm not going to say, like, who I've had whatever conversations with that have made me think this, but, like, you can go and experience this for yourself. Like, there's just nobody is superhuman. Like, we're all human beings. We all make mistakes. We all struggle to figure things out sometimes or whatever. Yeah. See, because even I'm not immune to it, right? Like, I grew up with the same kind of culture, and like I've wanted to be a mathematician since I was a teenager, right? So I still think, even though I've had all these experiences, a part of me is still like, but what if one of those people who's really superhuman is there in the chat and they're like, oh, this was obvious to me. I can't believe that you're even spending your time on this. Like, it's really insidious. Once you're raised in it. Oh no. Yeah. I mean, I don't really have much occasion to long multiply numbers, but I always found I think various groups claim credit for it. I think it's more popular in Asia, but I always found the method with the rectangular table to be nice. Like, I was, when I was a kid, I was taught to do like, I was taught to do like, the, like 123 times 45, and then, you go like this, right? But like, this thing is actually quite nice. I really enjoy this one, Wait, are you saying you should look up this? I'll show you this method of multiplication if you're curious about the multiplication. Yeah. So here, I'll do it more clean, and then I'll do this on a different page, and I'll do it more clean, and then I'll get back. It is just this. I mean, it is equivalent. It's just more organized, but like it does. It feels nice. So if I want to do 123 times 45, I think I should maybe do it on the other side in order to make it come out. So I'll do these boxes like this. Plus 1 point. So 100. So okay. So first, I just, in each of these little rectangles, I multiply the two corresponding numbers. So like 4 times 1 is 0, 4, because 4 is in the ones place. 5 times 1 is 0, 5. 4 times 2 is 8, 0, 8. 5 times 2 is 10, 1, 0. 4 times 3 is 12. And then 5 times 3 is 15. And then look, this was 5 times 3, so this is ones and this is tens. But then like up here, 5 times 100, I get 5 100s and 0 1000s and so forth. Yeah, so now just for my own edification, I'll finish. So like there's 5, and then our tens, we have 3, and then our hundreds, we have 15, right? So then I get a 5 here, and then a 1 carries up here. So I'm still doing the carries, right? Like, it's not like it makes you stop having to carry. And then I get 5, and then I guess it's that 5, 5. Yeah. and presumably, I mean, this is it's very similar to the other thing. Let's see. Yeah. I think 50, I thought 57, isn't 57 the Grothendieck prime? I'm not sure, but I've been telling people it's 57. Oh, it's 57, okay. So, it's, just pick a prime. People will pick 57, 51, those are pretty popular choices. 27 comes up every once in a while. Yeah. But, okay. So what was the thing with simplicial sets that I wanted to address, right? The thing with simplicial sets is that this order complex is a simplicial set. And so actually the thing that I wanted to ask, oh no, you've been telling students that 12 is a prime? Well, examples are really important for sure. Oh, that's really bad. Yeah, just because someone's studying software engineering doesn't mean that people who are studying software engineering should know that 12 is composite. Like they should still know that. It's, yeah. I'm sorry. That was really distressing to me. Like it's like you can't just that can't be allowed. Like you can't have someone who's supposed to be a software engineer that doesn't know. Like it's fine. Obviously, it's fine if somebody doesn't have to use what a prime number is for long enough that they forget. Like I can understand that happening. But like a student who's like actively taking math along with programming courses should definitely know that for sure. But okay, so okay, so yeah, if something wait, so what's the point if something isn't semi-prime, then it's not composite or something like that? Like if it, well, no, but I mean you should. I'm sorry, I don't understand. If that's a joke, I don't really understand, because it's like if you can factor it once, it doesn't matter. It doesn't matter if it factors more. You should know that it's not prime. Okay. Well, anyway, I'm gonna go back to the question about simplicial sets. So what's the deal with this? Or what's the deal with this order complex? It's actually that this order complex is a simplicial, is the like geometric realization or whatever you want to say of a simplicial set. Like this is coming from a simplicial set construction. And so so here's the thing, is that if I have here, maybe I'll not draw the picture again, but if I have a lattice L, then I can define a simplicial set, which will be I guess I'll call it n. I guess I'll call it n of L, which by definition, if we want to be fancy, is a functor like this. So it's a thing that has, or I think maybe, well, okay, I'll just call it n of L for now. So this has for its nth component, sum x1 less than or equal to x2 less than or equal to xn. Okay, now I have to. Oh, okay, so you already know. I have to make sure I get the right number of these less than or equals. Okay, I guess I actually want n plus 1. Such that all the xi's are in my lattice. Okay, and so in addition to saying, okay, so the little n-dimensional simplices are the chains of length n, and that's exactly what I had talked about up here, right? That's that. But okay, if you are so inclined, the lattice L is actually a category, right? So any lattice is a category where so what is the Hom set between two elements of the lattice? Those x and y are some elements in the lattice. They're objects in the corresponding category now. Well, there is a single morphism in this Hom set when x is less than or equal to y, and then otherwise it's just there's no morphism at all when x is not less than or equal to y. And remember, that doesn't mean that when x is greater than y, that just means, like a and b are not comparable, so they wouldn't have this. So, or another way of saying it is like this identification of the lattice with a category is just saying, here's my picture of my lattice, here's my Hasse diagram, right, that I've been drawing for this two-element Boolean algebra, lattice, whatever. Oh. Yeah. So it's just saying, well, okay, so what's going to happen? It's saying that that you just take all of these things in your Hasse diagram and you just say, those are the arrows in a category. Okay, and then we have to make sure that it's got the whole order relation, so we also have to actually have an arrow going like this too. But that's it. It's just okay, and then stick in all the identities, right? So it's just really turning the Hasse diagram into this messier picture. That's the okay, if you want to say it like this, that's the what I just did is saying that there is a functor from the category of lattices, like the variety of lattices, to the category of categories where homomorphisms between lattices become functors between the corresponding categories, and actually it's even a little bit more than that, because if you do this construction, like this will make the meet and join will be the product and the coproduct, and so actually like you have categories with products and coproducts, and the functors between them are preserving them, and so like it's even more special than that. But like, yeah, I mean, that it's all to say that lattices are categories. Yeah, okay, good. Yeah. So lattices are categories. Categories have nerves. The nerve of a category is like exactly like this, except instead of x1 less than or equal to x2, blah blah blah, it's that you have a sequence of morphisms from like maybe an object a1 to a2. So you have a sequence of composable morphisms. You have n composable morphisms that make up the n-dimensional cells. Okay, pretend that says an plus 1. And so those are what your simplices are, but then you have to specify how they're glued together in order to make a simplicial set, which is like some sort of a little bit of an abstraction of a simplicial complex, but not as wild as a CW complex, which is not quite as well behaved. I feel like I maybe I'm just not in the right spaces, but okay, that wasn't meant to be a joke, but maybe I'm not in the right mathematical environment for it, but like I feel like I don't hear people talk about CW complexes a lot. Like I feel like I see CW complexes more in older stuff. Am I just missing out on where CW complexes are happening, or like are CW complexes like not the current thing that people are into? Like I'm not really sure. Not really sure about that. I'm wondering if people like got tired of CW complexes. So like what definitely is useful is the notion of like I think people will call them semi-simplicial sets or like delta complexes, where it's sort of like a one-sided version of what I was just mentioning, because like in Hatcher's algebraic topology textbook, like he'll do like the calculations of like he won't do like the simplicial homology of like the torus directly, because you have to have a triangulation, and it's a lot of stuff actually to do it that way, like by hand. So he'll just do these like more these other gluings that are more like the simplicial set kind of gluings, and like that's actually fine for computing the homology groups. Okay, yeah, you find the CW complex is finicky. Oh, you have seen CW complexes in topological data analysis, and also they were in Morse theory stuff. Yeah, I'm not really sure about, like, just because I'm not an expert on either of these things, Morse theory or topological data analysis. I can tell you some things about each of them, but it's not something that I've ever like done much with. Definitely nothing really original. Besides the one thing I mentioned previously on the stream or on Mastodon or something. But like, yeah, I can't really speak to whether you need them for those things, or if it's just like what people tend to prefer for some reason. Let's see. Yeah, it's good that you're still steal as much food from presentations and conferences and stuff as possible. You need it to make it through grad school. So, oh yeah, you've seen I don't remember Hatcher's discussion of CW complexes. I just remember these he called them delta complexes. I think this is also what I've heard people call semi-simplicial sets before. But because it only has one of the two types of maps that there are. But like, what was I gonna say? Oh yeah, you know what I found, just for a future warning for people. I don't know if anyone's gone far enough in the algebraic topology direction to experience this, but even though let's see. Oh, are you saying you think the CW complexes can be convenient for the concrete attaching and gluing arguments? Oh, I remember the argument now. Okay, yeah, right. Because like if you want to construct a space with a certain fundamental group, right? Yeah, okay, I remember the example now. Thanks for reminding me. See, this is a point where it's like, oh, if I was superhuman, then I would have definitely remembered this without having to be prompted. So, it's like if you want to construct a space with a certain fundamental group, then the way that you can do that is I'm not going to give like an hour-long lecture on this because it's like a little bit of an aside, but like on this exact thing, right? So take a wedge of circles for well, okay, I don't need the arrow really, but like take a wedge of circles, one for each of your generators, right? So like whatever, I mean I have 4 generators, A, B, C, and D, right? And if I just wanted the free group, then I would say, well, if I look at paths in this thing, they all have to go through the origin, or this, you know, the center point, the wedge point here, right? They can't go anywhere else. And so, you know, I would just get the free group generated by A, B, C, and D. But if I want to now, you know, if I want to now force some kind of relations between them, then I can imagine taking a circle, you know, some circle that's like my 2 cell, right? And then if I glue it onto this thing, then that gluing can kill off any particular, like can enforce any particular relation that I want, right? Because like if you know, if I take it to be like, you know, I don't know, if I do like A B, you know, if I do like A B A inverse B inverse, for instance, right? And I make that I make that a cell, then that'll mean that the path that starts at the origin and goes to A and then goes to B and then goes back the other way around A and then goes back the other way around B, that'll actually be the identity. And so that means like A, I guess I have to orient it like this, whatever, but A, B, A inverse, B inverse is you know, the identity, because like you can you know, this will get rid of that element of the fundamental group, and so then it makes these 2 things commute with each other, and like, okay, so yeah, so alright, so CW complexes are good for this. I just haven't happened to have a particular use of CW complex in a while. But yeah, that's the reason that you want it. For whatever reason, when I first think of CW complex, the first thing I always think of is well, you know, I can you know, I can take my higher dimensional cell and like the gluing onto like the lower dimensional skeleton. I can like, you know, take this and I can make the boundary of it have to actually go to like, you know, like some horrible like, you know, like fractal that's like just completely like not, you know, not differentiable anywhere, and like things like that. Because why not? Oh yeah. Yeah, so if you can work with simplicial sets, then it's nice, because you don't have to worry about like, you know, what if I do something really unpleasant, right? Like, are you talking about Betty number, or? I'm actually not sure that I've heard Betty group before. So like the number, so when people started studying algebraic topology, I think they were more interested in the ranks of the free parts of what we now call the homology groups, and they weren't as interested in the structure of the groups themselves. And so they would study what came to be called, you know, or what were called the, you know, I mean, they're still called the Betty numbers, which were the ranks of these free parts, if I'm remembering correctly. and that was like the main thing that they wanted to know, because with like the usual like integral homology that does correspond in the familiar cases of like surfaces and stuff, like that does tell you the number of holes in like the in the sense that we would in the everyday sense that we would think of there being like a hole in the donut or whatever, and so that was the motivation. So I'm not sure. I don't remember hearing. I feel like I don't remember hearing Betty Group before, but it could just be that I haven't heard that word. Okay. I just have never heard that called the Betty Group that I can remember. But what I just described is correct. So Betty probably only looked at presumably there was someone named Betty who only looked at those groups and just looked at their ranks, and that's what the Betty numbers are. And like I've just never heard the term Betty Group for that free part of the homology before. So the question was, is this related? Oh, and thanks for telling me that, by the way. I've just never happened to hear that term before that I can recall. Okay, so the question is this related? Well, I mean, it's not, okay, so it's not like directly related. It's related in the sense that there are various ways of constructing spaces out of simpler pieces that follow this general paradigm of gluing higher dimensional things onto lower dimensional things somehow. But there's a couple different ways that you can do it that have different advantages. And some of them, okay, I guess this is the comment that I was going to make, is that some ways between like simplicial sets versus, CW complex versus like semi-simplicial sets, or like delta complexes. Like, they have various advantages or disadvantages when actually trying to do these calculations. So, it's maybe not too much of a secret that, like, you're not going to actually be able to directly get your hands on the singular homology of a space because, like, you're not really going to be able to directly examine all of the singular simplices very well because there's too many of them. And there's, like, all sorts of, like, really unpleasant, like, kinds of maps maybe to consider in like the general continuous case, right? You're not gonna do it. It's not gonna happen, except maybe in some nice cases. So you're gonna need some better way of computing the homology or cohomology, and it can be proven that if you compute it with, like, for instance, CW complexes like are being mentioned, then you can. Thanks for saying that you'll rewatch this. That's great. It makes me feel like I'm doing something useful here. But yeah, so like if you can show in theory that the singular homology or cohomology has to be isomorphic to the one that you get by doing like the CW one or the simplicial one or whatever, then you don't have to worry about computing the singular one. Even if you care about these more like continuous kinds of properties, it's okay. You'll get the same result. But there are some caveats here which can be painful when you go to actually try to do this in practice, because depending on your choice of which paradigm you're in, you will have a less pleasant time actually computing what the product is on cohomology, for instance. So I remember this because when I was in grad school, I was like, I'm going to sit down and use the delta. I wanted to look at some, like, actually now I'm trying to remember exactly what my ultimate goal was, but I was like, okay, I'm going to actually make sure I manually do some small spaces, like directly using delta complexes, right? And I'm going to compute their cohomology rings, and then I went to do that by hand, and then I found that with the delta complex way of presenting things, I wasn't getting what I was supposed to in order to give the product on homology classes, and so I couldn't get the cup product to come out the way it was supposed to be. And so then I talked, there's topologists around, right? And I'm like, hey, why is this not doing it? Am I doing it wrong? Like, why is this not working? And they're like, oh, well, you need to have an approximation to the identity. And I was like, to induce this map. And I was like, okay. And then I looked at that and I was like, okay, how do I get that in this setting? And I was like, I'm having a hard time, getting this to come out. And finally, I mentioned this to somebody, and he, to one of the topologists, and he was just like, oh yeah, I've never actually explicitly done this way before. I don't think you're gonna be able to write down that map. You're not gonna, it's not gonna be nice. You're not gonna have a good time, And I was like, oh, okay. So it can really bite you when you know that in theory all of these things should give you the same result, but some of the, I'm not going to say that the correspondences between these aren't constructive, because I don't have a proof of that, but sometimes it's really easy to compute, for instance, the product and cohomology in one of the presentations but not in the other one, and it doesn't seem like they're equal to each other in that respect. So in the simplicial side of it, computing the simplicial cup product, the cup product in the simplicial setting is very easy. It's very natural. But doing it in the semi-simplicial setting seems to not be as nice for some reason. I don't know. I encourage you to do that yourself if you want to see what happens. I don't know if I want to put myself through that again on the stream, but yeah. Yeah. So these things are all the same in some some specific senses, but it's definitely not it's definitely not even when things literally give you the same answers and the corresponding rings are isomorphic, it's not always going to be just as easy to do it one way as it is to do it the other way. Yeah, some of these tricks just won't work, even though it looks like it's a very similar thing. It's just, yeah, that's definitely true. Yeah, so I have less of an occasion. So my current manifolds project that I have going on, I have less occasion to look at the Durham cohomology, because although I do at part of the process in the construction for the paper that I have that has to do with manifolds, we do have something smooth, but the resulting object that we're more interested in is actually just a topological manifold. So unless the construction can somehow be repaired to make something nicer in certain cases, I don't have the smooth structure, and so, I mean, yeah. Well, I guess actually I'm not gonna go on about it. Yeah, I'm just not gonna go there. Yeah. It's like there's a measure zero set of bad points, but if you remove them, then you'll get something that's homotopy equivalent to a graph, just a combinatorial graph, and then you're like, well, I don't need anything too fancy, right? Because I can just study the graph itself. I don't have to study this, realization. Okay, so actually, it really depends on where you are in algebra because, like, in my opinion, like every grad student should have an algebraic topology course and learn like the the general story of like singular versus simplicial homology and what cohomology ring and like all of this type of thing. But like other than seeing those introductory applications to like why do we care about algebraic topology, some areas don't use it at all and some areas use it quite a bit. So even if you're in algebra, there's no guarantee that you're going to have a cohomology theory that's meaningful to you. If you're close enough to homotopy theory, then you're going to probably have several. But if you're far enough away, then you might not have any, or you might, you might only have one or two that you care about, but it just really depends. So definitely you can't expect that just because someone is a grad student in algebra, like for example, algebraic logic. People in algebraic logic aren't necessarily doing anything that, even though maybe there's some categorical way of interpreting it as topological, they're not doing anything that is like topological at all or homotopical, and so like they may not have any use of any kind of cohomology theory whatsoever. And they're algebraists. I mean, maybe logicians as well, but they're algebraists. And so it just really depends on where you are. You definitely can't guarantee that. I mean, there's, there are a great many things you can define that will be either formally generalized cohomology theories or just behave generally similarly to the familiar ones. And I don't know if anyone really does them all seriously. Yeah. Yeah, definitely. I see. There's agreement in the chat. I was just saying my piece and I hadn't read yet, but yeah, you definitely don't need to learn them all. It's not gonna, it's not going to necessarily be the case unless that's like literally the only type of thing that you do is study different kinds of generalized cohomology theories. And then of course also there's you can go further into it and start studying things like the Steenrod algebra and like these like different higher cohomology operations that like are beyond just the cup product. Or you could start doing, there's a whole bunch of people who do Hopf algebras that study the Hopf algebra structure where you have a co-multiplication as well. And, like there's an unlimited amount of directions that you can go with it. It's not like anyone's going to know every single thing about all of these things. It's just like, it's not something you have to do any of, but it's something that is it is pretty important or fundamental in a lot of parts of modern math for sure. Yeah, okay, so what was the actual question? Now that we're Dobby. Hey, what's up, buddy? Do you wanna know about cohomology theories? Do you want to compute things? Do you want to just sit there and do some real calculations like people do when they're doing real work? No, all he wants to do is just abstract theory. He doesn't want to compute anything. Okay, buddy. All right. He's like, okay, bud. He wants to be on the stream.
He's a star.
He's a star. Yeah, he is. He's our little celebrity. Stop trying to trick him. You don't need to be tricking him into thinking that there's a ball there. He has important things to calculate. So this is what I was wondering, which I'm not going to actually get to, I think, figure out very much in the stream since we talked about who's better at math or whatever, and a lot of generalities about homology. So like this was the thing that I was wondering about, was like, so the way that I defined this was by defining this family of maps from the lattice into the interval 0 to 1, which satisfied this condition that these sets f sub t were all principal downsets. And then with respect to this, I was able to actually give explicitly the meet and join of two elements of this thing in a way that would actually extend the lattice operation that I originally started out with. So that was the original thing. So now my question is, this felt a little bit like after the fact it didn't seem that bad, but it's still like overall it felt a little bit just ad hoc. Like obviously it works, it seems reasonably natural maybe after the fact, but like what I was wondering was like can I convince myself that actually there is a definition that it, oh wait, I went further than I wanted to. I want to convince myself that is there a definition that I can think of on the order complex itself, like on the nerve itself, that should induce the lattice operations as actually being like I want an operation on the actual, like on the nerve as a simplicial set, right? So like I want the meet and join to take to take things from this simplicial set and give me back other things in a way that is like compatible with how the simplicial set works. And I suppose that well, I guess the thing is that I have to think about if I wanted to do this in the way that I was thinking. I guess I have to think about products, which I haven't thought about for a while. But now I'm getting scared that products of simplicial sets are not going to give me something that I'm going to be happy with, because if I'm gonna have if I'm gonna have a binary operation, so I have a binary operation which is meet that takes pairs of things in this lattice to other things in this lattice. If I want to extend this to be a binary operation on that thing I was calling the nerve, then if I want to make such a simplicial map, which if you wanted to get technical was actually so remember a simplicial set is a functor from this simplex the opposite of this simplex category to sets, right? And so I would need that there was one which is the thing that is this thing, right? And then I would need a different simplicial set which was this, which should be like, if this is going to be like the proper categorical thing, this should be the product in the category of simplicial sets of these two things. And there should be a natural transformation between those two functors, which is like my meet, right? Like that's here, the meet should be like that. And so this is what I was wondering, but the reason I'm scared I'm scared of this now is because I'm remembering that so if I just have a pair of combinatorial simplices, right? So maybe here this is ABC, and then this is I don't know, UV. Then okay, the product of these as a topological space is so the product of these is going to be this prism, right? That's what this looks like. Okay, but in order for me to so this is clearly a simplicial complex, right? Because this is the simplicial complex that has just the facet, like, ABC. Right? So it's like subsets of ABC. This is like subsets of UV. But then, if I want to make a simplicial complex structure for this, well, it seems like that's not quite as natural, perhaps, because this is what the product should be. But how do you divide this up into simplices that are made from this? It doesn't seem maybe quite as obvious. And so this type of thing is a bit annoying. So instead, there will be lines diagonally through ABC across U, and so here's like AU, BU, CU, and AV, BV, CV, and, well, I mean, wait, so you're saying lines diagonally through coming from ABC across U. So diagonally, like, I'm sorry, I'm not sure like what the diagonal thing is here. Like, if I choose to do a line diagonally, like, yeah, like I can make a simplex that has AU, BU, CU, and AV as like the 4 vertices, but then like I have to make sure that I've covered the rest of the shape, and it seems like it's a little bit of a pain. I mean, maybe even another example is like take here's an even smaller example, right? Take the product of AB and UV, just those things. We should definitely get a square, and so the square is like AU, maybe AV, BU, BV, and so you can go like that and say, I have 2 simplices, but like, how do you explain why you got those 2 simplices? Like, at first it seems like that's fine, but like when you start doing a higher dimensional cubes like this, you're going to be like, wait, like, how do I actually figure out which of the simplices? I mean, this is a similar issue already. How do I figure out where I'm supposed to put the simplices? How do I combinatorially make this from the things that I had before? And so that's what's starting to sketch me out when I'm like, oh, I want the Cartesian product, because now I'm concerned that I want the Cartesian product of the geometric realization of the nerve, like that order complex, but I'm not going to be able to actually represent that as a, like, I'm not saying for sure, I know this for sure, but I'm concerned that I'm not going to be able to represent that as a simplicial set in a natural way, because I want the product of the spaces, not like the join or something. So k simplices of the product are like k minus n across n simplices, right? Well, okay, so then the question, so I guess the thing is that I want, so okay, so it's not, so actually I'm not sure off the top of my head whether that identification will give you the categorical product of 2 Yeah, so it could just be that I haven't looked at this enough myself as well. I'm not sure, so like no worries, brainstorming, because that's what I'm doing too. I obviously just for the sake of the exercise, I don't want to just like go look up right now, like while I'm in the last like 15 minutes of streaming, like the the categorical product of two simplicial sets. But the reason I'm concerned is basically this: is that if I can give a simplicial set description of the meet and join operations, that should induce a map from the product of the spaces that are the corresponding geometric realizations of this thing. So I should take the product of the geometric realization with itself, or maybe it'd be better to say, I'm not really sure about this situation over here, but I know that what I need is something that's from the what I might call delta of L, the actual order complex is a topological space. I know that I want a map that goes from this to itself that is a continuous map that is the meet operation. And so I know how to describe that explicitly, as others have before, like in the paper that I referenced. But what I was wondering was, is there a cleaner description in terms of simplicial sets? But what is making me concerned is that I need the simplicial set, which is like the product of these two topological spaces. But because products of topological spaces, okay, this one happened to be nice because it was small, but in general are looking like not wanting to be easily broken down into simplices, like combinatorially, even if they were simplices originally. That's what has me a little bit concerned. So I'm thinking that it may not be possible to do it this way. What can be done instead, which I'm not sure if this is the same thing up to homotopy or what the deal is, but what can be done instead is what's called the join. So you're saying the geometric realization commutes with finite products of. Okay, so you're saying that if I call it geometric realization delta, you're saying that delta of this is supposed to be or I guess I called it delta of L here, but yeah, it's supposed to be this. Is this equals to, or you're saying that that's the homotopy equivalent? What type of equals is this? That's a homeomorphism of spaces? Okay, you're gonna double check? Oh, I'm gonna double check. I see. I thought you said let me double check, but I see. Okay, I will. Okay, so the claim is this. Okay, if that's true, then that means that if I wanted to define this, I can actually just get a map on here and then define it that way. Okay, so that would be helpful. But then the question is, what is this? Because if there's not a natural way of defining the meet on this from the lattice L, then oh yeah, because I guess it's that the nerve construction. Okay, so all right. Okay, so now what I'm thinking is, okay, so this isn't the way I was originally thinking of it, but if I take the nerve of L squared, what does that look like? Well, the objects of L squared are like pairs of objects, like X and Y in L, and then the nerve, like what is like an n cell of this thing? It would be like a sequence. X1 is less than or equal to X2 is less than or equal to blah blah blah. It's less than or equal to Xn plus 1, and Y1 is less than or equal to Y2 is less than or equal to blah blah blah. It's less than or equal to Yn plus 1. And okay, so that's the nerve. The nerve consists of an end cell is like this, and so an end cell is like a pair of such cells. So if you have one of these n-dimensional simplices, then it's a pair of n-dimensional simplices from just L. But then if you, let's see, so it's a pair of such simplices from L. And then on the other hand, if you had a pair of things like this, it would give you it would give you one from L. Okay, I see. So I think what I've decided is that this looks like as sets that these n simplices should be in correspondence with these n simplices. But this has got to be compatible with the boundary, the face and the boundary maps as well, because I'm just doing that by inserting. I'm just doing that by inserting a repeated element or deleting something. Okay, so I'm tempted. Oh, this is squared. So I'm tempted to say that this should commute with products, and therefore, if I had a map from, so if that's correct, then if I have this map from L squared to L, then that should actually give me a corresponding map from n of L squared to n of L, but that I could identify this with n of L squared, and so that would be such an operation. And so, okay, so what would that be telling me to compute? That would just be like saying, take a simplex like this, and if you want to do the meat to it, just do it pairwise. Does that still work? Because if I know x1 is less than or equal to x2, and I know that y1 is less than or equal to y2, and then I do x1 meet y1. Well, sure. Like meet is you know, is isotone. It's non-decreasing in each of its components. So this has got to be less than or equal to x1 or x2 meet y2, and so that means that actually that looks like it makes sense. Okay, so there's like details to check, but that actually looks like that makes sense. Okay, so if that's correct, then that means that we have an operation on the nerve itself, which is this operation, which is just saying like do this to pairwise to lists of non-decreasing lists of elements. And then the thing would be, I need to figure out, okay, so then I would need to use this. If this is a homeomorphism, then I need to use this homeomorphism in order to get this map that I wanted. And so, okay, so I would need to know the homeomorphism there. And so, okay, so it's like, if I have two simplices like this, and then this would give me another simplex, another two simplex over here. Then I need to know what the product. I need to know what the product looks like. Oh no, this is, I see. This has got to be what the product looks like as a simplicial set, because, okay, this is bothering me. I think I'm not sure yet what this product is supposed to be, because if I did a really simple example where I had the simplicial set that just corresponded to the line here and the line here, I should get something that looks like it's like two-dimensional, right? But if I can form the product by just pairing up simplices from the same dimension, then it doesn't look like I'm getting any. I have to figure out how I'm getting non-degenerate two-dimensional simplices from that, because I guess it would be like, no, because it's like, okay, so if I only have, okay, so it's like the reason I get two-dimensional things, even if I started with one-dimensional things, is because even though I can't make like, so it's kind of like I can't make a non-degenerate list of like, say my elements are just like 0 and 1, I can go like 0 is less than or equal to 1, and then I can only pad it with more things that are like this, and so it's like that's all I can do. But if even though I can only do like okay, so even though I can only make like 0 is less than or equal to 1, 0 is less than or equal to 0, or 1 is less than or equal to 1, when I pair them together, yeah, so when I pair them together, then I can start doing things that are like 0 is less than or equal to 0 is less than or equal to 1, and 0 is less than or equal to 1 is less than or equal to 1. And this isn't just, sorry, well maybe, no, maybe that's still, no, it's not, because I'm not duplicating, that's the thing, is I'm not duplicating either entry, right? This less than or equal to isn't a trivial one, and neither is this one when they're considered together. So I think that's what makes it have things in the image that aren't degeneracies in the product, is because you didn't just get this by duplicating whatever is appearing next to it. This is actually different. Okay, so what that means then is that okay, so yeah, I really appreciate this pointing this out. This is what actually got me to go through to the rest of it, I think. So okay, so I understand what the product of the two simplicial sets is now, and that means that I can describe explicitly what it is, and I know how it's identified with, so I know what that is, but now I need to understand how the geometric realization of that is identified with the product of the geometric realizations of the individual ones. And so it's like, I can think about this as being like a single 3 simplex, but I can identify it with something that is in the product of the corresponding thing. Okay, this I'm still uncertain about, actually. The map between these two is the thing that I don't know. I don't know if I understand yet what that's doing. So I'll look that up though, because that's about it for time. But yeah, as always, I really appreciate everyone coming out. I thought it would be less busy because it was Memorial Day, but we had a lot of good discussions, and you know, we actually talked about some math here. We did more topology than I think we've ever done here before, so that was good. And you watched me figure out what the product of two simplicial sets was, maybe, if I did it correctly, and you know, it seems like it was pretty cool. I hope that you all have a awesome rest of your day or evening or no, it's not Memorial Day, it's Labor Day. It's one of them. I hope that it's awesome, and I just really appreciate you guys coming to see what we're doing, and you know, say hi to Dobby, and it's always a lot of fun. So yeah, I really appreciate it, and I hope that things continue to be awesome for you out there wherever you are. All right, well, yeah, thanks. I'm gonna call it here, I guess. So I'll see you all next week with a new paper, hopefully. Well, a new old paper. I'll explain next week, and I'll tell stories and stuff. It'll be cool. All right, see ya.